I'm Eunbyung from Sangkyugan University in South Korea, and so last couple of years I've been working on 3D computer vision and also including NeRF and 3DGS and also generative modelings. Anyway, originally as the first speaker, so today the topic would be some compact representation for 3D Gaussian splatting, which I believe is very relevant to this amazing workshop. So as many of you already know, if you just run the original 3DGS implementation, and if you train on some large-scale scene, then it would require about 1 gigabyte. Now, I think already the Mike already mentioned this. If you take state-of-the-art techniques, then it would take maybe 10 megabytes or 20 megabytes. So it's around maybe 100x in, I think, this 1.5 years. So it's been really quite a journey, and I'm super excited about the progress that we have made so far. So anyway, so today's plan is first, I quickly introduce the 3D Gaussian splatting, but I'm just gonna make it really quick. And then I'd like to introduce some motivations and also share my experience in this direction. And also I would like to review some of the recent papers along this line. So then let's get started. So this is 3D Gaussian splatting. I think everyone knows this feature. This is from the original paper. There are a couple of important components, and first one is the initialization. And so 3D Gaussian splatting is basically 3D Gaussian, and each Gaussian has many attributes. Here, mu is the position, and S and Q is a scalar notation, which determines the shape of the Gaussians. And also, this O is opacity, which determines the how much the Gaussian contribute to the actual rendering. And then finally, you have color information. The original version used spherical harmonic coefficients for representing view-dependent colors. And once you have a 3D Gaussian, now you splat or project to the 2D image plane, given the camera pose. And you have some differentiable rasterization to render the pixel. And there's another algorithm which is called adaptive density control. So initially, the number of Gaussian is quite low and very sparse. And so it's not really enough to express fine details and intricate details of the scenes. So they have some algorithm to gradually increase the number of Gaussian to express the high frequency details of the scene. This is a figure that shows the difference between NeRF and 3DGS. So it's essentially, if you look at the equation, it's essentially about the same. But difference is that in NeRF, when you shoot the ray, and then you have to sample multiple points along the ray. But in 3DGS, you have explicit 3D representation. So you only consider explicit 3D representation close to the ray. So that's one of the reasons why 3DGS can be much faster. So this is the performance. First, it's a super fast rendering, and also it's very fast training. The original version, it would take around an hour to train a large scene, but nowadays, if you look at the recent works, then it's about under 10 minutes, or sometimes under 5 minutes are enough to train the model, and also a really high quality rendering. And in my opinion, most importantly, this is open source. And I think Michael mentioned a lot of applications. So if you take this open source, and then if you take picture of your scene, and if you run the original implementation, it works really well. So that's probably one of the reasons that this technique has been so popular in many industries. So anyway, that's a quick recap. And I'm gonna move on to the real topic of the day. So the problem is you run the 3D Gaussian splatting and you get the too many Gaussians. So there are many issues. So obviously, first issue is that, as I said, each Gaussian has many attributes. And this is a bicycle scenes. And if you run the original algorithm, then it would require about 5 million Gaussian, which is large number of Gaussian. And then if you calculate the actual size, then it would around more than 1 gigabytes. That's the first issue. And the second issue is a slow rendering, because you have too many Gaussian. And when you render, this is rendering equation. If you have more Gaussian, you have to consider more Gaussian when you render. So obviously here, the n is the number of Gaussian you have to look at. So more Gaussian, you have to spend more computation. And another issue I think is also very important is that it's overfitting issue. So 3D Gaussian splatting is basically optimization process. And if you have more Gaussian, which means that there are more parameters that you need to train. So it's likely that you overfit the training view, but the goal is to render the novel views. And because we have more parameters, and these parameters are highly optimized training view, and sometimes you lose some generalization ability. So in this example, the left one, you have 2 million Gaussians, and right one is about 1/3 of Gaussian, and you can see that it improves the PSNR. So now I'm going to introduce some of the techniques that I have worked on. So first, the problem is the number of Gaussian. So what we try to implement here is that anyway, we need to figure out which Gaussians are important and which Gaussians are not important. So here we apply some binary mask. It's basically non-order mask, and we use some traceable estimator to make it differentiable. So it's going to be end-to-end trainable. And we have used the information of opacity and the scale. So opacity is about how much contribution each Gaussian for the rendering, and scale is about the size of Gaussian. So both information is quite important to figure out which Gaussians are important. And this is a training process. So the green line is the original 3D Gaussian splatting, and then red line is our proposed version. The original version usually is top densification at around 15K iteration, and then we apply our method, and then it gradually decreases the number of Gaussian. But we keep, we don't actually sacrifice the rendering quality, and also we improve the rendering speed because we reduce the number of Gaussian. So that was the number of Gaussian, and as I said, each Gaussian has a lot of attributes. So we need to be able to compress those attributes. And then first one is about the shape. And then here is a visualization when you train the Gaussian. And then if you look at the Gaussian distribution, and we initially thought that there is not much locality we can take advantage of. So we we propose to use some vector quantization. So among the many techniques, we use the residual vector quantization. And if you're in the compression community, you might be familiar with this technique. This is a technique that many deep learning-based compression methods have used. And so another one is color. And so each Gaussian, the color has occupied most of the space, especially it takes 48 dimension for spherical harmonic coefficients. But the color, unlike the shape, it shows locality. So meaning that if you have neighboring Gaussian, it tends to have similar colors. And so we need to have some representation that has some spatial locality, and also we need to have some representation we can correct the color very quickly. So here we decided to use instant NGP, which is based on hash-based grid and also small MLP. And this is a very compact representation. They use some hash collision method to compress the three-dimensional tensor. So here is the overall pipeline. First, we have 3D Gaussians, and then we remove the Gaussians that are not really necessary and also redundant. And also, we slightly adjust the Gaussian shape by using some residual vector quantization. And finally, we query the color information from the instant NGP. And then eventually, we have full representation of 3D Gaussian splatting. And finally, we go through some rendering process. And this entire process is end-to-end trainable, and we try to find some optimal representation for compact 3D Gaussian splatting. So this is the qualitative results. Here, PP means the post-processing. We apply some hop-found coding and also bit quantization to further reduce the spatial complexity. So finally, performance is about 27 in 360-degree dataset, and also we reduced the storage from 700 megabytes down to 25 megabytes. So here's some example of static scenes. We also apply this technique to the dynamic scenes too. So now I would like to introduce the other great works too. Here, this is the light Gaussian, which was published last Nuris. And if you look at the entire pipeline, it looks a lot similar to what I just described. And it has some 3 stages. And first one, it has some pruning and recovery stage. They develop a technique to tell which Gaussians are important. They call it as a Gaussian significance, and they consider a lot of information here. So intersection means that so how much pixels that particular Gaussian actually affect when rendering, and also they consider opacity and also transitance and Gaussian volume. And similarly, they also consider compressing this high degree spherical harmonic coefficients, and then they use some distillation techniques to reduce the spatial complexity. And finally, they also use vector quantization. So here's their performance. I'm just gonna move on. There's another paper. I think this is also concurrent work. As you can see, the pipeline is a lot similar, and they have vector quantization here, and also they have quantization for color, and then they have some quantization-aware fine-tuning, and they also apply some techniques from some point cloud compression, such as sorting, and also they apply some entropy coding. So far, so we have some lessons. So first, learner masking or pruning. So basically, we need to know which Gaussian is important. And second, we don't have to have a full degree of the color information. That's for sure. And also because each Gaussian is basically a high-dimensional vector, and we can apply some vector or bit quantization. And finally, you can apply some entropy coding. Whenever you apply entropy coding, then you can gain another 30% improvement. So here's another great work, Scaffold.js. I guess many of state-of-the-art methods are actually based on this method. And one special thing about this method is they use the latent attributes instead of the low attribute of the Gaussian. So each anchor point, the anchor point is the representative points of a group of Gaussian. In this case, one anchor point can generate 4 Gaussians. So each anchor point has its own feature, and this latent feature or latent attribute goes through the MLP, so small tiny neural network, and then this tiny neural network actually generates the rest of the Gaussians. So that it can only maintain Okay, is it okay? Yeah. I'm just gonna move on.
Yeah,
So anyway,
please continue.
yeah. So they have latent attributes, and then these attributes also go through a small neural network, which is decoder, and then this decoder generates the low attributes of the Gaussian. And in particular, they apply some progress training, and then they start from the low resolution training, and then they increase the resolution along the process, along the training process. And this is a performance of the Eagles, and they achieved about the same performance, and also in this case, they also claim that they achieve very fast training time. So here we learn about the latent attributes and also anchoring process, and also I think the progress training is quite effective. So another recent work, which I think this is really great, is a mini splatting. So here's the example of the leftmost figure is about the Gaussian distribution of the original 3DGS algorithm. As you can see, there is a small cluster around the points, and if you look at their mini splatting version, and you can see more uniformly distributed Gaussians, and so the reason why this is happening in the original 3DGS algorithm is basically first they start from the sparse point cloud, and then they gradually increase the Gaussian around the original point. So you can see many blobs in the sparse point cloud. Now they develop some blur split, also depth initialization, and another technique to make it some uniformly distributed. And this is going to be much more efficient than the original version. And this is their performance. And they said that they can achieve better compression ratio than the previous work. And nowadays, there are many recent works that touch on the densification algorithm. For example, mini splatting version 2, taming 3DGS, and also recently TurboGS. They are talking about the inefficiency of densification algorithm and also training algorithm, the original version of training algorithm. So if you're interested, please take a look this great work. So another lesson, so better densification algorithm is really important. And so far, there are many progress, but there are some missing components. So I would like to introduce this particular work, which is hash grid assisted context. So if I talk to someone who are working on compression, then this context modeling is basically by default. So if you look at some learn image codec and also learn video codec, all techniques are using this context modeling. What that means is that so eventually at the end of the day, we are going to do entropy coding, and this entropy coding is based on the entropy. So entropy is about the uncertainty, and so in this context modeling, what it does is that for a particular Gaussian, if you can predict the attribute of the Gaussian, then what that means is that you are very certain about the Gaussian attribute. So if you can predict better attributes, then you can reduce the entropy, and then it will lead to very high compression ratio. So that's basically context modeling, and this work, as far as I know, the first introduced the context modeling in the 3DGS representation. And here's their performance, and I think this is very impressive, and they outperform all the previous work by a large margin. This is another work, the context GS. As name suggests, it's also about modeling context. And based on the previous work, you also use Scaffold.js, and it uses more advanced version of context modeling. In this case, they use auto-regressive context modeling, and also they leverage some hyperprior techniques that has been developed in image and video compression community. So here is their performance, which outperformed the previous work. So here are the lessons. I just compiled all the techniques that we have seen so far. And so some of the techniques might be quite useful. So when you try to implement or develop your own algorithm, maybe, and then if you need to care about some efficiency of your representation, that you might want to incorporate some of the techniques into your algorithm, and they would improve your efficiency. And if you really push the limits of the compression, then probably you want to print all the techniques into together. I think I have maybe 5 more minutes, and this is the last paper, which is called Self-Organized Gaussian Grid, in short, SOG. When I talk to some people who are working on some standard, I think this is a technique they would really love. And the reason is that they use the existing 2D image compression codec. So here's what they did. So basically, 3D Gaussian, each Gaussian is a high-dimensional vector, but it's in the 3D space. But in order to use 2D codec, they have to reduce down to the 2D. So what they did is that they used some techniques from point cloud compression, which is basically, they call it as a sorting. So here, here is an example of the images, and so each image is also high-dimensional vector, and then they rearrange these images into 2D space. So similar images are close each other, and so if you're different, then it's going to be far away. Then once you construct this 2D grid feature representation, then you can apply existing 2D image codec to compress this representation. And here is their pipeline, and there's some iterative process, and in the middle is try to maximize some locality of the 2D grid representation to make the 2D image compression later will compress much better. So I'm almost done. So here is a slide. I think you probably already know. So someone already compiled many existing techniques into one place, and then there's also a survey paper. So please take a look. And this is the final slide, and I'd like to end this talk by discussing some of the future works. Some items here is obviously not entirely new. Many people are already working on these directions, but I think this some technical innovation might be really important to make progress further. So first one is the dynamic 3D Gaussian splatting. There are tons of work and tons of papers, and then they're really great. But I think if you think about some fast-moving or fast-changing dynamic scenario, we still need to have some techniques to improve more efficiency. And the second one, I think I'm quite interested in, is the streaming and on-the-fly encoding. So if you think about some live streaming of dynamic 3D scenes, then these techniques is going to be really important. And third bullet is memory efficient 3DS. So far, we have talked about only the storage requirements, but at the end of the day, we want to render this representation on a small smartphone or edge devices. So in that case, this working memory is really important. So we have to be able to have some really great representation to be able to run on those edge devices. And another one, nowadays, there are a lot of primitives are coming out. For example, texture.js, convex splatting, and also 2D Gaussian splatting, and so on. So some of the techniques that I introduced today might be applied to those new primitives, but I think more specialized algorithm might be useful for those recent primitives. And finally, learn encoder and decoder, which means is that so far all the compression, 3GS compression algorithm is based on the parsing optimization. And as I mentioned, there are some works about context modeling. But if you really want to do context modeling, we have to rely on some large scale data set. So from the large scale data set, we learn data prior, and then based on this prior, we can do really great context modeling, which improves the compression ratio. And I've seen a couple of papers coming out recently, and some recent Fit4 compact 3GS paper, they try to this idea to make it more faster and also make it very more compact. And also, obviously, there are much more directions. I think I'm done today. Thanks for your attention.